So let's see what happens with friction. We'll continue with the same problem from the previous example, but we will actually add friction uh, to the block and the table. So once again, we have a 4.0 kilogram block rests on a horizontal table. After a force F with a magnitude of 50 newtons and an angle of 25 degrees with the horizontal is applied to it, the block begins to slide across the table. In this example, however, we're going to have friction. And so if the kinetic coefficient of friction between the block and the table is 0.2, once again, we will find what the acceleration of the block is. A lot of the steps are very similar to what we did in the previous example. So if you haven't watched the previous videos, please go back to that video and watch it. What we did was we started with Newton's second law in vector form, but we really immediately wrote down that relationship with the components x and y, which eventually gave us the solutions, the equations of motions for the block. Here's the block once again. On the horizontal table, we had gravity, normal force, and the force, the pulling force, the 50 Newton force that acts at an angle of 25 degrees. The new element here is that I have to draw a fourth vector here, a new extra vector to account for the friction, and that has to point to the left along the horizontal direction, because we know that whenever we have sliding, that is kinetic friction, and the kinetic friction always opposes motion. We know that the block will be sliding across the table to the right, so the kinetic friction will be to the left. I will be working with the components of the forces, so once again I will choose a coordinate system, a very natural choice here for x to be to the right and y to be upward. Once again, let's go around the vectors and see what their components are. We saw from the previous example that the components for gravity were 0 and minus mg. The components for the normal force were 0 and what I called plus Fn, since I didn't know the value from the beginning. The new element here is that the frictional force also has components. And here I'm going to write it above the vector since I didn't have space. The friction acts along the horizontal direction. So it's going to have a horizontal or x component, and in fact it's going to be negative because it points to the left, opposite to my choice for positive x. I'm going to write that component as minus F friction, and it will have no y component, so that will be the 0 here. And going back to the force F, the 50 Newton force, it had two components, Fx and Fy, which we worked with those Fx and Fy, and we saw that using trigonometry, we can easily figure out what they were. Here we pulled the vector on a separate diagram, and we saw that the x component was the adjacent and the y component was the opposite side into that little right triangle, and because of that they had for Fy to be F sine theta, or 21.131 newtons, and for the Fx to be F cosine theta, or 45.315 newtons. With that, we were ready to actually go to the equations that emerged from Newton's second law. We start with the x components. We have to add all the x components to write down an equation. The x components for gravity and normal force were 0, remember? So we start with two zeros, plus the x component for that force F, that I called Fx. And here I also have to add the x component for the friction, which is minus F friction. And that has to be equal to max. So here I see that my equation that emerges from the x components requirement from Newton's second law is that I will have F cosine theta minus F friction has to be equal to m times the x component of the acceleration. And here is where I can show you how we cannot take that equation and get to the x component of the acceleration immediately, because we don't know how much the frictional force is. Unlike the previous example where technically we could jump into this equation and get the answer right away, here we have to be patient. So let's go to the y components. Remember, all gravity and normal force and the other force and the force F had y components. So here, what I had before in the previous example was that I had minus mg plus Fn plus Fy, and technically I have to add the component for the friction, which is 0. So I end up with an equation that simply says minus mg plus fn plus f sine theta has to be equal to may. So there are my two equations of motions that emerge from Newton's second law. For the x, I had f cosine theta minus f friction has to be max, and for the y, I had minus mg plus fn plus f sine theta is equal to may. Now I have extra variables. I don't know what the frictional force is. Technically, I still don't know what the normal force is. But remember, we're dealing with sliding block along a table. So we're dealing with the kinetic friction, and we know that the kinetic friction actually depends on the normal force. We might not know its value, but it's not arbitrary. In fact, when it comes to kinetic friction, we always know that the magnitude of the kinetic friction is always a fraction of the magnitude of the normal force. How much that fraction is determined by the kinetic coefficient of friction, which we call mu here, and the problem tells us it's 0.2. So this relationship links the friction and the normal force. So the unknown in our equations are not as many as we might think at first glance. Once again, the question here will be about acceleration, and we have the equations of motion, so we're ready to actually start solving for the problem. Here I copied the equations for the x and the y. Remember, in the x equation, we have the symbol for the frictional force, but the frictional force is going to be mu Fn, a fraction of the normal force. In the previous example, I used the equation that emerged from the x component, and I can start with that equation again here. I have f cosine theta minus the frictional force has to be max. So, but here's where I'm stuck, and I see that in order for me to find the x component of the acceleration, I need to figure out the frictional force first. So because of that, I have to go to the second equation, minus mg plus fn plus f sine theta is equal to may. Remember, even though here we had fn and ay as unknowns, we can have only one or the other, but never both simultaneously as unknown in our equations. Once again, a very natural guess that turns out to be the correct guess is to assume that the block slides along the table. The problem itself says so, and that we maintain contact with the table, so that we are going to guess that the block remains in contact. In other words, that the y component of the acceleration will be 0, and we will have a normal force. So you can see that this equation is exactly the same as the previous example. Nothing has changed. Adding friction along the horizontal direction has not changed anything about the balance in the vertical direction. I will have minus mg plus fn plus f sine theta has to be equal to 0, just as before, which gives me, just as before in the previous example, for the normal force to be 18.1 newtons. The new element here is that now, since I know the normal force, I can actually figure out what is the magnitude of the y component of the, what is the magnitude of the frictional force, which turns out to be equal to the x component of that friction. But anyway, frictional force, when it comes to kinetic friction, is going to be equal to mu times Fn, or 0.2, according to the problem, that's the kinetic coefficient of friction, times 18.1 newtons. So I see that my frictional force is really equal to 3.62 newtons, pointing to the left. So that is going to appear to be its x component. So with that, I can go back to my x equation here up in the right corner and start putting numbers. F cosine theta will be 5 cosine of 25 minus the frictional force, which is 3.62 newtons, and everything has to be equal to 4.0 times ax. So now I can see that for the x component of the acceleration, I will have 10.42 meters per second squared, which is going to be the answer in the problem, but let's write it down in a proper way. With these equations of motion, I have determined that the y component of the acceleration is once again 0, the x component is 10.42 meters per second squared, so the magnitude of the acceleration is 10.42, or here you can round to 3 significant digits, 10.4 meters per second squared, with a direction to the right. Once again, notice that the normal force is 18.1 newtons, which is exactly the same value as in the previous example. Adding friction did not change the magnitude of the normal force.